Welcome to another VCE Physics coaching video. Today we are looking at changes in gravitational potential energy of an object moving in a gravitational force field. So first of all, if you've completed Unit 2 Physics, you've already studied this a little bit to the extent that gravity is considered constant if we're moving over small enough distances close to the Earth's surface. So I've sort of shown that graphically here in the top left. You see that this line here is constant no matter what the height. So here, if I can just draw like a little house, and we assume that the gravitational field lines over a small enough distance are parallel to each other. Gravity is attractive, so it's moving downwards. So effectively, the change in gravitational potential energy is effectively the area under a rectangle, and that leads to the formula change in gravitational potential energy is mg, the force due to gravity, times the height change. So it'll increase in gravitational energy if it's being raised, the object, or it'll decrease if it's falling. And that might be converted to kinetic energy. And in turn, due to collisions with the air, to heat, light, and sound. Now, in Unit 3 Physics, we just take a step back a little bit and imagine we're looking and seeing the Earth a little bit curved in nature. So I'll draw the house there a little bit smaller, and over a larger distance, you'll notice the field lines are starting to spread out a little bit. And of course, gravity is attractive again. So the force of gravity gets lower as you get further out. So it's looking at it a bit more differently, or a bit more expansively in Unit 3 Physics compared to Unit 2. And correspondingly, the graph will drop off too. In accordance with an inverse square relationship, this graph looks a bit more circular than inverse square, but it's a good approximation. Two ways we can measure the energy changes. Both use a graphical approach. And the first one we'll look at on the left is that the change in energy is the area under a gravitational force versus distance, or I've got R for radius from the center of the planet. If it's distance, if the graph shows the altitude above the planet, then you've got to add the radius of the planet. Just be aware of that. It might be an extra layer of complexity. But let's do an example. The energy equals the area under the graph. The way we do it, it's equal to the number of squares under the graph. I'll show you what that means in just a moment. So I'll write that number of squares times the area of one square. So it involves counting squares. So there's one square there. I'll come back to that in just a moment. And we've got to define the distances over which the object might be falling. Let's say it's from 3 by 10 to the 6 meters. Notice that's by 10 to the 6 meters on the radius axis, and it falls down to 1 by 10 to the 6 meters. So they're like the limits of integration. This is really a graphical, basic integral calculus approach. So we count squares 1, 2, 3, 4. If the square is more than half covered, we've got just slightly more than half a square, then we count it. If it's under, then we don't count it. So 1, so we've got 4 there, 5, 6. We'll count that one. That's right on. That could be arguably just under actually, but we'll count it. That's 7. We've got a little bit there we could add in, but I've counted 7. And then we multiply that by the area of one square. So that becomes 7 squares. And the area of one square, well, that's on the vertical axis. So I've got 20. That's that 20 multiplied by 1. And important to remember this scaling factor here, by 10 to the 6. All right. Now, if you multiply all of that out, we get 1.4 by 10 to the 8. And the units of energy is a Newton meter or joule. So the change in gravitational potential energy is 1.4 by 10 to the 8 joules, which is a fairly large number. Okay, so the other way we might be required to do that is by not looking at a gravitational force versus distance. The graph might be presented in a gravitational force per kilogram. Okay, that means we can just use one graph and we multiply it by the mass of the object in the field. So in this case, we've got a 20 kilogram meteor, let's say, falling towards Earth from a distance of, say, 3,000 kilometers down to about 1,000 kilometers. Again, we've expressed our limits of integration. So in this case, the change in energy would be done a little bit differently. So it's the change in energy is equal to the area under the graph times mass this time. This time we've got to multiply the area we're going to determine by the mass. The reason is because it's the vertical axis is a force per kilogram. We need to multiply it out by the number of kilograms. So this is a more generic graph, which is perhaps a bit more versatile to use because that would be the same graph for a given planet. And then we just multiply it by the mass of an object in that field. Whereas this graph on the left is more specific to one object. And you might get either in an assessment task or a question. So let's look at that. The area under the graph would be, so it's a number of squares times the area of one square times the mass. So if we count squares again, so 1, 2, 3, 4, that one's slightly over. We won't count that. You can see that would probably fill in that if we wanted it to. 5, 6, 7, that one's just slightly over. In this case, you could easily make it 6.5 squares, actually. You could make a case for 6.5 squares. Also, in an assessment task, in the VCEA exam, there's leeway given for square counting. So take as much care as possible, but there is some leeway given. For example, plus or minus 10% on the final answer. But if you show the working out carefully, then that will help tremendously, which we're supposed to do in any case, show the working out. So I've counted 7 squares again. And so we'll write 7 squares times the area of 1 square. That's 1 by 1 by 10 to the 6. Times the mass of the meteor was 20. So if we multiply all of that out, we again get 1.4 by 10 to the 8, and that would be joules. So remember that this might also be asked to be expressed in megajoules, which would be about 140 megajoules. That could be asked for as well. So there's 2 different ways of calculating the changes in energy. So it's a bit more complex than in Unit 2, but it's possible to do with a little bit of care. Just note the way we've laid everything out, showing our working with care. So I hope this video is helpful to you. And this is in the first area of study. Some schools might look at the first area of study after doing the first 2. So just be aware of that. So in the meantime, thanks for watching another VCE Physics coaching video.